Introspect technology product showcase. Today we're presenting the Introspect
DesignCon 2019,
very compact, high
Santa Clara Convention Center.
High parallelism test instrument for high-speed interfaces, and we'll focus today on 28 gigabit per second NRZ and 56 gigabit per second PAM4. So by way of introduction, Introspect makes test equipment, and the way we go about making test equipment is to try and address gaps in the existing marketplace and the existing tool space that's available for our users. So traditionally, the equipment space has been divided between traditional bench equipment like oscilloscopes, bit error rate testers, and network analyzers on the left side. But then once people go to production, you would transition to automatic test equipment for wafer probing and functional testing. The problem with this paradigm, of course, is that as the development processes become more complex, you start to need more and more tools through various stages of development. And you often see cases where you bring ATE equipment into the lab, or you take bench equipment into the factory floor. So Introspect was born out of this problem. It was born to create what we call a hybrid test and measurement solution that could be deployed in a lot of circumstances. So our equipment generally is very high performance, but as you'll see today, it is very, very compact. So at our product showcase today, we're showing our parallel 28 gigabit per second NRZ tester, and in PAM4 56 gigabit per second solution as well. So this is a parallel BERT. It has pattern generation on individual channels. It has jitter injection, receiver testing, receiver characterization capabilities in a very, very small form factor. And it's also able to measure device transmitters. We'll see today measurement of things like eye diagrams and jitter functions. So the product, I'll just put the product slide here. It's in summary, it's a parallel test system. It has continuous data rate coverage, so it can test anything from 10 gigabit per second up to 28 or 56 gigabits per second. Each channel out of its pattern generators has its individual voltage controls, its individual jitter injection controls, and pattern controls. So it's really like multiple sets of instruments in a single box. And then finally on the receivers, it's based on hardware clock recovery, so it can track low frequency jitter and enable you to measure compliant eye masks in a system-oriented manner. So we'll go ahead now and start showing the product and show software that works with the product. So what we have here in our setup is the test system. We've connected a couple of channels to a device that's hidden inside this black box here. So the instrument itself is on the left and the device is here. And we'll start with NRZ signaling, and then we'll transition over to PAM4. The instrument is completely controlled by PC through a USB bus. And so everything that I do here is just a USB communication that goes from the PC to the instrument. And the software environment for the instrument is Python. So we have a nice Windows graphical user interface, but under the hood, it's completely automated in Python. You could use it in Python to Python environments, or you could use it in a semi-manual way here. So you're all welcome to come closer to see how it works, but I have here a very simple setup where I declare a pattern generator and an error detector. And so I declare a pattern generator by defining a component called TX channel list. And that component basically is where you declare the channels that you want to play patterns on, the kinds of patterns that you want to play, as well as any impairments that you want to create. And then I'm declaring a BERT scan function to measure the transmit eye opening. And we'll start with this simple test, just a simple two-line program here that I'll just execute. And when I do that, we'll just see the result pop up. And so here's the result of measuring a device transmitter at 28 gigabit per second in almost instantaneous fashion. In this particular setup, I've actually injected jitter on the pattern generator. So you could see a very wide shoulder of jitter here. That's SJ that's produced by the instrument going through the device and being measured back. So we're demonstrating pattern generation, we're demonstrating jitter injection, but we're also demonstrating the ability to very rapidly collect a bathtub. This was extremely instantaneous. If I do it again, in less than a second, I'm basically collecting a very deep BER bathtub on the product. And so that's for production testing. This is a very attractive feature of the instrument. I can go ahead now and demonstrate automation and how we could change how the system behaves. So I will actually go and dynamically add a command to say, I want you to stop playing the jitter injection now. I still want you to generate the traffic, generate the test pattern, but turn off the jitter injection and show me what happens to the transmit eye. So I just commented out a couple of commands here. I click run on it. We'll see two bathtub plots now. The first one is the original one that I had set up. That's the pattern generator producing the traffic and producing sinusoidal jitter on the signal. And then the second one is when I asked the pattern generator to stop injecting jitter. And let's see what the eye looks like. And you could already see that the eye opening is more in the case of no jitter. And I can overlay both plots on top of each other and show that one of them basically has a wide opening and one of them has the characteristic sinusoidal jitter shoulder. And so the idea here is, again, with Python automation, you're able to just sequence through a lot of characterization tasks, a lot of characterization tests very, very, very rapidly. So we'll go ahead now and maybe add another dimension to the testing by demonstrating eye mask testing. So I've kept the transmit, the pattern generator the same, and I'm saying instead of giving me just a horizontal eye opening, I want you to shmoo the entire eye and give me both horizontal and vertical, potentially to put a mask on it. So we'll just go ahead and run that again. And so during this run, we'll see the flow of the architecture of Introspect in general. You have the first tab in the software is where you program your script, your automation script for characterization. When you're executing a script, it goes into a log tab, which is an activity log really, and it's telling you everything that it's doing. And then when an execution is finished, it goes to a results tab, which records the measurements that you've made. And one of the things about the results tab, if you have noticed, is that every time I made an execution of the program, it created an entry in a table, and that entry is a folder that exists in your file system and that's always present. So the data in this system is completely open. You could extract the data in Python and use it in your own analysis programs, or you could even analyze results offline. So my last execution has just finished, and if you remember, I said I wanted to repeat the bathtub measurement, but I also wanted to do an eye diagram now on the data. I want to see more than just the horizontal eye opening. I want to see horizontal and vertical. And so this is the result that came out, and you can see it's a characteristic eye diagram shape. But if you're familiar with sinusoidal jitter injection, you'll immediately recognize the signature. This is basically the sinusoidal jitter injection going through the CDR that we're testing and still coming through the output. And we're demonstrating basically how much transfer the CDR that we're testing is producing, how much of the sinusoidal jitter is actually passed through. And so this is a typical production test. If you're creating CDRs for optical cables, or if you're creating transceivers in general, this would be a typical production test as well. You create a set point jitter injection profile, apply it to the device in mass production, and see if your process variation is maintaining a certain jitter transfer function. And so we'll go ahead now and, just for the sake of completeness, demonstrate the eye when jitter injection is turned off. And the purpose here will be to show the noise floor of the system and the signal integrity. We'll see a very open, very clean signal eye at these speeds.
So can you define like a pass-fail test for this using the software?
Yes.
To create like a binning of when you do like in production?
Absolutely. So the question is, can we define pass-fail testing within the software? And the answer is yes. In Python, what we're showing here is just a visualization of the result, but in reality, all results are stored in Python classes that you could get access to through accessor functions. so 10 more seconds, and then we'll transition to the final, final step of this demo. So, okay, so here's the eye with jitter injection, and then the eye on the right is basically the clean eye without any jitter injection. And so you can see reproducibility. Each one of these graphs that I'm popping up here are new acquisitions. They're new measurements being taken on the device. And so you could compare the clean eye with no jitter injection with the impaired eye. And so on top of jitter injection, of course, we have voltage impairments and things like that that we can demonstrate offline after the showcase. For the last part of this session, we'd like to introduce our PAM4 capability. This is relatively new territory for us, but using the same instrument, we're modifying how the connections are made, and we have a device inside the box there that will show us a PAM4 response. So I just started an execution here, and we'll start to measure an eye diagram for PAM4, and we'll show some of the characteristic features of our PAT Gen for PAM4 and some of the measurements as well.
Is it a PRBS pattern that you are passing?
Right now we're doing the PRBS pattern, the two-phase PRBS pattern for PAM4, yeah. But it can generate any pattern. It has pattern instruction sequencers inside, so you can generate traffic, you can generate anything you want. And so it just popped up now, the response of the device inside the box, and so here's a PAM4 eye diagram. From a generation point of view, this system has DACs on every pin, and so we're able to do linearity testing, for example, on PAM4. We're able to adjust the levels for each of the 4 levels of the PAM4 eye. And as well, we're able to do a jitter injection, just like I showed in NRZ. We're able to do sinusoidal jitter injection or even phase injection on PAM4 signals. So everything that I've showed in NRZ is fundamentally the same in PAM4. So I think I'm just about on time, so I will conclude this showcase, and I will thank you everyone again for taking the time to stand with us here for this 15 minutes. Thank you.
Once again, Mohamed Hafed, CEO of Introspect Technology at DesignCon 2019 in Santa Clara, California.